Welcome back. In the last session, we talked about the concepts of what k-nearest neighbor is that it is a memory-based model, and the fact that it is non-parametric. And what we are doing now in this session is that we're going to apply this into the iris datasets, just so that we can actually get an understanding of how it actually works. So let's start with some code. So I'm gonna import our usual import numpy as numpy import pandas, and we're gonna need the seaborn, and we're gonna make use of scikit-learn, the datasets itself, because within it does actually have the iris dataset as plt percentage matplotlib inline, and we're going to set the style as white grid. All right, so the next thing now is that we do want to load the datasets. So load the datasets, and calling it iris matplotlib pyplot. Okay, and let's have a look at visualize the data a little. Okay, so that's fine. All the basic things is there. Okay, so let me just copy my codes here. The first thing is that, again, we're just gonna look at the petal as well as the length and width of the features. We won't use all of the features for now. We're just looking at the petal length and also the width itself. And we're just going to convert the species from string to integer, just so that the scikit-learn library can actually perform its computation easily. We're just using a simple map function that comes with pandas to map the species to the actual numbers. And we'll just do that conversion based on the definitions that we've done here in this dictionary. For Setosa 0, versicolor 1, Virginica 2. Of course, you can actually specify any way you want to. And then once we've done that, we are just going to store the species columns, which is the converted species column, the 0, 1, 2, and we stored it into our Y train. The X train will contain our petal length and petal width information. The Y train will contain the species. Won't be in the form of string. It will be in the form of the integer that we've defined. All right, so let's start importing the sklearn. And from sklearn the neighbors library, we're going to import the k-nearest neighbor classifier. And we're just going to instantiate this. Knn is equal to our k-nearest neighbor. 1, 3, and we're gonna say we need 5. So the question that you might have is, what does the k here or the n neighbors here actually mean? We can always open up the scikit-learn documentation and try to actually understand this. So what it actually does say over here is this. The principle behind nearest neighbors method is to find a predefined number of training samples closest in distance to the new point and predict the label from the. I guess the other way that you can actually say this, the k in the knn or k nearest neighbor means the number of neighbors in the actual space you want your new data to be compared to in order to classify. Okay, so that's really the basic idea here. So here we want to actually look at 5 to compare it to in order to classify this. All right, so let's fit that to our X train and also our Y train. I'm aware that there's a typo here. Okay, that's been fitted without problem. The only thing is that we can't really visualize this, so we don't really know what happened. So I'm gonna just use a code that I already developed earlier on, and I'm just gonna copy and paste it across here. We have the X train, the values, and we just store this into X values, and then we separate out the high and the low on the x-axis and the high and low on the y-axis, and we just basically create a mesh, and then we run the actual predictor, the KNN predictor on the x and y, and store that into Z. Z is going to be our line a little later on. And we plot the figure, and basically a three-dimensional contour that we are plotting. Finally, the actual scatter of the actual pedal length and width itself. So let's just run that. And this is actually what you see. You have the Setosa here, if you do recall. If I remember correctly, this is Virginica, and then I can't remember what this is, Visicolor. Okay, so you have this line here is the actual edge colors. Okay, looking at this, you can actually see the segregation between the three classes. There are some mislabeling, but nevertheless, you can actually see that it actually does it is able to actually segregate the three classes pretty well. Of course, we can actually vary the number of neighbors to actually force it to actually define a bit better. But it doesn't seem like actually makes much of a difference. Obviously, when you actually have a smaller number, you're likely to have more errors, and it's going to be overfitted quite obviously. So that's really the end of this lesson here on this. But before we go, I would like you to actually make some more variation. Try the nearest neighbor to see if you can actually vary this a little bit, as I did, and see what kind of change in terms of the so-called plot here, in terms of the boundaries that will change. So I'd like you to actually play around with that. The other thing is that just a little bit of food for thought before we go away, and I'd like you to watch this, is that there is obviously a leaf size, but the matrix here is the Minkowski that I want you to pay attention to. When we come back, we're going to focus on that a little bit, but for now, vary the actual number of neighbors to see what kind of lessons you can draw from that. So pause the video now. When you come back, I'll talk to you with that a little bit more. Alright, welcome back. I hope you played that around a little bit, and just to actually get a little bit further intuition. You can probably gauge by now that KNN is a really simple classifier, and one that you can actually implement into any data sets very quickly, and you will be able to actually get certain amount of accuracy with it. Bearing in mind that you might have some drawback in terms of when it actually applies to real world data, especially if you have large data set, that it may slow down a lot. So that's really the basics that I want to actually get across in this lesson. For now, the main lesson that we can draw from this is the fact that it is very simple to implement. It's very straightforward. You just feed the actual X-train data and Y-train data, the actual classes, and what you get is actually a segregation of the different classes. And when we come back, we're going to go into a little bit more about the documentation. How is the actual so-called separation done, and we're going to specifically look at the different type of distance measure that you can use on top of or different from Minkowski. So with that, I'm going to stop right now. I look forward to talking to you in the next video. Thank you for watching.